Hi everyone, Mrs. V here, and today we are going to be talking about the pH scale and how to calculate pH values. So let's get our whiteboard on and get started. You've probably heard about pH values and you've probably heard about the pH scale. And pH itself is just a measurement. It's a quantitative measurement, so it's numbers. It's actually a numerical scale that talks about the acidity or basicity of solutions. So whether something's an acid or a base. And we have a scale that goes from 0 to 14. 7 in the middle of that scale is neutral. So our neutral point is 7. Anything that's above 7 is called a base. And anything that is below 7 is called an acid. You would have your very, very strong acids down around pHs of 0 or 1, as long as they were concentrated strong acids. And then you would have your concentrated strong bases at the other end of the scale. There are some, you can get negative pH values, so you can get values outside of this scale, but we normally work within the 0 to 14 scale. So just measures how acidic or basic something is. You may have used universal indicator in the past to look at the pH of solutions. Universal indicator is a mixture of different indicators, so it gives you a great range of colors. So here we see that the red color, we're looking at strongly acidic here. And in the middle, we have neutral. And right down at the violet end, we have the strongly basic substances. And in between, I guess we have the orange and the yellow just being weakly acidic. And the blue and turquoise are sort of weakly basic. But you can get a nice range of colors out of that indicator, so it's fairly useful indicator if you're trying to work out the acidity or basicity of substances. The pH scale ranges from 0 to 14, so just remember 7 is neutral, pH less than 7 is acid, and pH greater than 7 is base. And the way we calculate pH is we calculate it with from the concentration of H3O plus in a solution. And you'll remember H3O plus, or the hydronium ion, is a hydrogen ion attached to a water molecule. It's actually a logarithmic scale, so pH is calculated by minus the log of the concentration of H3O plus. We've used those square brackets to mean concentration for a while now. So this means if we had a solution where the concentration of H3O plus was equal to 0.1, that would be in moles per litre, then pH will be minus the log of 0.1, which is 1. Now it's a logarithmic scale, which means something with pH of 2 will be 10 times less acidic than something with pH of 1. So we have a look at the concentration of H3O plus. If that was 0.01 moles per litre, then the pH would come out to be minus log of 0.01, which is 2. So every time you go down 1 point in pH, you actually have 10 times the acidity. So the pH scale, logarithmic, each pH value below 7, each 1 point is 10 times more acidic than the next one. Let's do some real example calculations. We're going to be dealing in this video with strong acids and bases. And what that means is that their ionization is considered to be complete. So we have 100% conversion of reactants to products. Well, this is what we assume. It wouldn't be that way in reality. And we assume the position of equilibrium is all the way over to the right. So we'll do a monoprotic and a diprotic, and I think you'll be able to work the triprotic out from there. So our first example is going to be a strong monoprotic acid. We're going to find the pH of 0.030 moles per litre, nitric acid. When we write the ionization equation for nitric acid, we would normally write with an equilibrium arrow. However, in this case, we are going to assume that that is all the way over to the right, so that we have completely converted the HNO3 and the H2O into H3O plus and NO3 minus. And that's important because now we can assume that there is a 1-to-1 mole ratio between the nitric acid and the hydronium ion. And what that allows us to say is that the concentration of H3O plus is the same as the concentration of the acid. This is only possible for a few acids. They're very, very strong acids that we can make this assumption. And that means when we calculate our pH by minus log concentration of H3O plus, we just have the concentration of the acid in the H3O plus. So this is 0.030, and if we run that through the calculator, we're going to get a value of 1.5. So you can see fairly low pH. It is a strong acid, although there is a concentration aspect to pH as well. So pH depends not only on how strong an acid is, but also how concentrated it is. And 0.030 moles per litre is a pretty dilute solution. So we don't have a pH down around 0. We're looking here, still fairly low pH, but 1.5. All right, next example, let's do a diprotic acid. And in this case, we're going to be looking at sulfuric acid. So let's find the pH of 0.025 moles per litre sulfuric acid. Now you'll remember sulfuric acid has 2 ionization steps. So its first ionization step is sulfuric acid reacting with water to give the hydrogen sulfate ion and the hydronium ion. Then the hydrogen sulfate ion goes on further to form the sulfate ion and another hydronium ion. So one sulfuric acid can produce two hydronium ions. Now, in reality, the Ka value for the first step is a large Ka. So that actually goes to completion. But the second step is a small Ka value. But for the purposes of using this method of calculating pH, we're going to have to assume that both of those have very large Ka values. So what that means is we're only going to get an approximation for this. So we can approximate the pH using this method, but it won't be completely accurate. And that's because of that small Ka on the second step. So we'll continue as though we're assuming that both of those steps go to completion. If we assume complete ionization, then one sulfuric acid can react with two water molecules and you'll get two hydronium ions. So that means that our mole ratio now between the acid and the hydronium is 1:2. And what that means is that the concentration of hydronium ions is going to be twice the concentration of sulfuric acid. And in this example, that's going to be 2 times by 0.025, which is going to be 0.050 moles per litre. From there, we just continue with pH as minus log of concentration of H3O plus. That's minus log of 0.050, and that comes out to be 1.3. But remember, that's just an approximation. So the pH of 0.025 moles per litre sulfuric acid is approximately 1.3. I will show you in future videos how you go on and do that absolutely properly so you can get an accurate answer. But for the purposes of this, we'll just assume that complete ionization. All right, example 3 brings us on to how do we do the pH of bases. So we're going to do a strong base here. And for a strong base, we're looking not at the concentration of H3O plus out of the dissociation of the base, but the concentration of OH minus. So here we have 0.15 moles per litre potassium hydroxide. So this solution was produced by some solid potassium hydroxide dissolving in water and dissociating into those ions. And here we see we've got a 1-to-1 ratio between the potassium hydroxide and the hydroxide ion. So the concentration of OH minus is equal to the concentration of potassium hydroxide. And in this case, that's 0.15 moles per litre. But pH doesn't tell us about the concentration of OH minus. But once we know the concentration of OH minus, we've got two different methods that we can use. So method number 1, I'm going to call the KW method. So you'll remember that Kw is the concentration of H3O plus times by the concentration of OH minus, and that equals 25. That equals 10 to the minus 14 at 25 degrees. Now, if we know the concentration of OH minus is equal to 0.15, then we just substitute that in and we can find the concentration of H3O plus. So concentration of H3O plus, concentration of OH minus is equal to 10 to the minus 14. What that means is that the concentration of H3O plus is equal to 10 to the minus 14 divided by the concentration of OH minus. And in this case, the concentration of OH minus is 0.15. And that will give us 6.7 times by 10 to the minus 14. What we do then, that will be in moles per litre, of course. Then, now that we have concentration of H3O plus, we can go minus log. It's minus log of 6.7 times 10 to the minus 14. And if we express that to two significant figures, we get 13. So that's our first method, the KW method. Our second method I'm going to call the POH method. And in this case, we use POH. If pH is the concentration of H3O plus, or minus the log of it, POH is minus log of the concentration of OH minus. So from this example, we find the POH, which is minus log of 0.15, which comes to 0.82. Then we use the fact that pH plus POH always adds up to 14, and we can derive that from KW. But we'll just use this formula, and therefore pH is equal to 14 minus POH. So 14 minus 0.82 using correct significant figures is going to give us 13 again. So it doesn't matter which of those methods you use, you're going to get the same answer. And that is how you do pH of strong bases. I think that's enough for this video. I will see you in the next one when we are going to talk about how to calculate the pH of weak acids. I'll see you then.